Stuxnet was discovered in 2010, and we called it the first cyberweapon. That framing may have just aged badly by about 15 years. Researchers at Sentinel-1 presented findings at Black Hat Asia this week on a piece of malware they're calling Fast16. The short version: it appears to target engineering and physics simulation software. It tries to induce computational errors in those simulations, and based on code artifacts and compilation timestamps, Sentinel-1 believes it predates Stuxnet by roughly 5 years, putting its likely creation somewhere around 2005, possibly earlier. If that dating holds up under scrutiny, Fast16 is not just older than Stuxnet. It represents a fundamentally different, and in some ways more insidious attack philosophy. Stuxnet was kinetic in intent. It targeted Siemens S7-315 and S7-417 PLCs, manipulated centrifuge spin rates, and caused physical destruction while feeding operators false normal readings. The sabotage was real, but the mechanism was eventually findable because centrifuges were physically failing. Fast16 goes after something softer and harder to detect: the integrity of simulation outputs. If your simulation software is quietly producing wrong answers, you might not know for months or years. You just ship a flawed design, or you trust an engineering calculation that is subtly off, or you make a safety decision based on data that has been quietly corrupted upstream. There is no physical debris to find. There is no centrifuge that stops spinning. There is just a number that is wrong, embedded in a decision that has already been made. The specific targeting here matters. Engineering and physics simulation software means tools like MATLAB, ANSYS, COMSOL, or similar packages used in industrial design, structural analysis, fluid dynamics, and yes, nuclear and weapons-adjacent applications. We don't know from the reporting which specific software packages Fast16 targeted. Sentinel-1 has not publicly named them, at least not in what's been published so far, and the press coverage is thin on those details. What we do know is that the attack surface is simulation pipelines, not the control systems themselves, which is a meaningful distinction. You're not attacking the thing that runs the plant. You're attacking the thing that tells engineers whether the plant design is safe. Now, a few things to hold with appropriate skepticism before you start catastrophizing. Malware compilation timestamps can be manipulated. They are not cryptographically authenticated. Dating malware by its artifacts is an inference, not a proof, and sophisticated state actors absolutely know how to fake or obscure those timestamps. Sentinel-1 has strong incentives to present this as a historically significant find because it was presented at a conference, and that is how conference papers and security vendor research works. That is not a reason to dismiss the finding, but it is a reason to wait for independent corroboration before treating 2005 as established fact. The register piece is largely a rewrite of the conference presentation. Unclear from the reporting whether any independent researchers have reviewed the sample or the dating methodology. That said, even if the dating is off by a few years, the operational implications are real and they are not being talked about enough. Here is the uncomfortable thing about simulation layer attacks. Industrial control system security has, over the past decade or so, gotten somewhat more serious. There are ICS-specific security frameworks. There is network segmentation guidance. There is air-gap discipline, at least in theory. SCADA systems are increasingly monitored, but the engineering workstations that run simulation software, those often live in a weird middle zone. They are not fully air-gapped because engineers need to collaborate and share files. They are not fully on the corporate network because IT doesn't really own them. They run software that is updated infrequently because the software is expensive, the licenses are complex, and nobody wants to break a validated simulation environment by patching it. And they often run old operating systems. If you have ever tried to get an engineering team to update MATLAB on a machine that is running a validated workflow, you know that conversation ends with the engineer explaining why that is not happening this quarter. Fast16, if it is real and if the targeting is what Sentinel-1 says it is, would have been nearly invisible in that environment. There are no signatures to catch simulation output corruption. Your EDR is not going to alert on a result that is 3% wrong. Your SIEM has no telemetry from the physics solver. The only way you find this kind of compromise is if you are doing integrity checking on your simulation outputs against known good baselines, and almost nobody does that systematically. The 15 years undetected framing in the headline is actually the part worth sitting with. not as a scary number, but as a structural observation. If a piece of malware targeting simulation software ran undetected from 2005 to now, that is not primarily a story about one clever piece of malware. It is a story about a monitoring blind spot that the entire industry has. We have gotten reasonably good at detecting malware that does things. Exfiltrates data, encrypts files, moves laterally, calls home. We are much worse at detecting malware that corrupts the integrity of computations quietly and leaves no obvious trail. That class of attack is harder to find, harder to attribute, and harder to remediate because you don't know what decisions were made downstream of the corrupted data. For teams running OT or ICS environments, or teams that support engineering workstations in any industrial, aerospace, defense, or energy context, there are a few concrete things worth doing right now. First, inventory your simulation software environments. Know what versions are running, know what operating systems they are on, and know when they were last patched. That sounds basic, but a lot of organizations genuinely do not have this. Second, think about whether you have any integrity verification on simulation outputs. If two independent simulation runs of the same model should produce the same result, are you checking that? If you have historical baseline outputs, can you rerun them and compare? Third, treat engineering workstations with the same network segmentation discipline you would apply to a PLC. They are not just developer machines. They are part of the control and design chain. And fourth, if you are in a sector where simulation integrity matters for safety, this is worth a conversation with your engineering leadership about whether historical simulation results should be revalidated for anything that went into production in the last decade or more. The real story here is not that one piece of old malware got found. It is that we have been implicitly assuming simulation layer integrity for years, and that assumption has never been verified at scale.